Hi, my name is Dimitrios and I will be presenting balance allocations within complete information, the power of two queries. This is joint work with Thomas Sauerwald from the University of Cambridge. We will start with some background on sequential allocation processes. So in this setting, we need to allocate m tasks or balls sequentially into n machines or bins. And the goal is to minimize the maximum load. So for this load vector here, the maximum load is 5. And this is equivalent to minimizing the gap. The gap is the distance of the maximum load to the mean. In a centralized setting, this problem is trivially solved using the round-robin allocation scheme, which achieves the almost perfect load distribution at every step. However, in decentralized settings, we look at allocation processes that require less coordination between the bins. And this finds several applications in hashing, load balancing, and routing. The simplest of these processes is one choice. So for each ball, you pick a bin uniformly at random and you allocate the ball there. In the lightly loaded case, that is when the number of balls is equal to the number of bins, the gap is log n over log n with high probability. Here with high probability we mean probability at least 1 minus n to the minus c for some positive constant c. In the heavily loaded case, that is when the number of balls is much larger than the number of bins, the gap is with high probability square root m over n times log n. And you can think of this as roughly the maximum load of n independent Poisson random variables with parameter m over n. A great improvement over this is the two-choice process, where for each ball we pick two bins independently and uniformly at random, and we allocate in the least loaded of the two. In the lightly loaded case, this process has a gap of log n. And if we compare this with one choice, this is almost an exponential improvement. In the heavily loaded case, the improvement is even more dramatic, as the gap bound remains the same, and this means there is no dependence on m. There are several other processes, one of which is the 1 plus beta process. In the 1 plus beta process, each ball is allocated with probability beta using two choice and with probability 1 minus beta using one choice. Mitzenmacher interpreted this as a two choice with some probability of making an error in the comparison. Perez, Talvar, and Vidar proved in the heavily loaded case that the gap is log n over beta when beta is sufficiently large and it is bounded away from 1. We are now ready to introduce the processes that we focus on in our work. So in the adaptive one threshold process, we pick a threshold based on the entire load vector at time step t. Then we sample a bin. If the bin load is below the threshold, then we allocate there. Otherwise, we allocate in a second bin chosen uniformly at random. So we pick the threshold. If the bin is below the threshold, we allocate there. Otherwise, we allocate to a random bin. Of course, the second bin could be worse than the one we picked first. For the lightly loaded case, Feldheim and Gürel-Gürwitsch determined the optimal threshold and proved that this achieves the square root log n over log n with high probability. They also conjectured that the same bound extends to the heavily loaded case. For the special case where the threshold is equal to the mean, it was recently shown that the gap is log n with high probability. A related process is the adaptive one quantile process. So in this process we pick a quantile based on the entire load distribution, and if the bin is on the right of the quantile, then we accept. Otherwise, we take another subpoint. It is easy to see that adaptive quantile process can simulate any adaptive threshold process by setting the quantile at the place where the loads are equal to the threshold. It is also possible using a mixture of two threshold processes to simulate any adaptive quantile process. And it turns out that both are special cases of the two-thinning process, of which there have been several extensions where you can take up to d samples. Another view of adaptive one threshold is as two-choice with incomplete information. This means that we can only compare two bins if one bin is above the threshold and one bin is below the threshold. So these bins we can compare. These bins are both above, so we cannot distinguish, and these bins are both below, so we cannot distinguish. Of course, we can also view quantile as two-choice with incomplete information, but here the regions are in the rank space, not in the load space. So these two we can tell apart, and these two we cannot. Using this incomplete information interpretation, we can extend one threshold to have multiple thresholds. And this means we can only distinguish bins if they're in different regions. So these two bins we can distinguish. These two bins are in the same region, so we cannot distinguish. And Iwama and Kawashi analyzed the lightly loaded case, where when the thresholds are chosen so that they are equidistant. In our work, we mostly focus in the heavily loaded case. And of course, a similar extension works for k-quantile. But again, the regions are in the rank space. So in our work, we disproved the conjecture by Feldheim and Gurevich, and we show that any adaptive one quantile or one threshold process has with high probability an omega log n over log n gap. And we also define a k-quantile process with uniform quantiles. This means that the quantiles depend only on the number of bins, and this achieves a k times log n to the 1 over k gap. So for k equals 1, we get a log n upper bound. For k equals 2, we get a square root log n. And because of the lower bound that we have, we get a quadratic improvement when we use two queries instead of one. And this is what we call the power of two queries. And for k equals 3, we get cube root, k equals 4, fourth root, and it approximates two choice as k increases. In particular, for k being theta log n, we recover the two choice with up to multiplicative constant factors. And we also analyze the case for 1 plus beta when beta is close to 1. In particular, when beta is 1 minus poly n, we show that the gap is log n. By majorization, we are also able to show that there is a process for d-thinning which achieves a gap of d times log n to the 2 over d. And for graphical allocations in dense expander graphs, we show that the two choice achieves a log n gap. And this makes progress towards the second open question by Perez, Talbot, and Vider. Our proof techniques make use of layered induction over exponential potential functions, and we think this will be useful. This might be useful for analyzing other processes. Now we're ready to go in the proof outline for the lower bound. So we're going to show that any adaptive quantile and equivalently adaptive threshold process has a gap that is at least log n over log n in the first n log squared n steps. So we consider two cases. First one is that the process uses at most n quantiles that are large. So in this case, it means that we're using mostly small quantiles, and in turn this means that the first sample is used often. And in particular, it means that if we pick this lower bound to be 1 over log squared n, then it means that the process disagrees with one choice in at most linear allocations. So by Poissonization, we can show that one choice has at least omega n bolt above m over n plus omega log n. So even if we reallocate all of these, then still we cannot reduce the gap below log n. And the second case, we have at least n quantiles which are large. And this means that if we break the allocation into intervals of n balls, then there will be one which has at least n over log squared n balls with large quantiles. And this in turn means that if we look at the n over log n heavier beans, then we are doing one choice over them. And by properties of one choice, we get that the gap is omega log n over log log n. We are now going to introduce the k-quantile process and give an outline of the k log n to the 1 over k proof. So this quantile has the median quantile for coarse balancing, and the rest of the quantiles are placed in the region of heavy beans. In particular, the quantiles are increasingly dense over the heavy beans, and this is what allows for fine-grained comparisons among them. So in our proofs, we make use of the two-sided exponential potential function as a base case, and this was used by Perez, Talver, and Wieder to prove the upper bound for the 1 plus beta process. So for each bean, we have the exponential of the normalized load smoothed by a factor alpha. And the second term is the negative of the normalized load. So for 1 plus beta, alpha was chosen to be theta of beta, and PDW showed that the exponential potential drops by a multiplicative factor when it is sufficiently large. And using this drop inequality, one can prove using induction and the Taylor law of expectation that the expectation of the exponential potential function is c times n for some c that depends on c1 and c2. And by Markov's inequality, we can get that the exponential potential is at most c times poly n with high probability. And this implies, because each of the terms of the exponential potential is positive, that the gap is at most log n over alpha. For small alpha, the drop inequality is easier to prove, but the gap bound becomes worse. In PDW, alpha was at most a constant, so the tightest gaps proved there were of the order of log n. Talver and Wieder used this as a base case, so the log n gap, in order to prove, to analyze the two-choice process in the heavily loaded case. And they did this using an extension of the layered induction. However, we will take a slightly different approach, and we will do this layered induction over super-exponential potential functions. So super-exponential means that alpha is multiplied by a super constant value. And this is what will allow us to prove the sublogarithmic gap bounds. However, we don't get that the exponential potential drops unconditionally on every step. We have to condition on this good step event, which says that the delta k minus jth quantile value is at least that small. And again by induction and the Taylor law of expectation, if we start with the log n gap bound, and we know that in an interval with the length n times polylog n, then after that many steps, the expectation becomes linear. And in order to get this good step condition, observe that if we know that the exponential potential is linear, not just poly-n, then we can get an upper bound on the bins that have a load at least some value. And similarly, if we condition that phi jt is linear, then we get the good step condition for j plus 1. And this will be the key step in the layered induction. Let's see in particular the case for k equals 3. So let's start with phi 0 being linear, which implies that the maximum load is at most logarithmic. It also implies, by looking at the number of bins above cube root log n, that the value at the delta 2 quantile is at most cube root log n. And this is the good condition for phi 1. So phi 1 drops in expectation until it becomes linear. And it being linear implies that the gap is at most log n, cube root log n plus log n to the 2/3, which is the dominating term. And it also implies an upper bound on the delta 1 quantile. In particular, that delta 1 quantile is smaller than 2 times log n to the 1/3. And this is the good step condition for phi 2. And hence we get that phi 2 drops until it becomes linear, and then we could get the 3 times cube root log n upper bound. It remains to show how to convert the expectation of phi j being linear into phi j is linear with high probability. And we assume that in an interval of length n times polylog n, by induction hypothesis, every step is good, and also we have every step the expectation of phi jt is linear. Then, by Markov's inequality, we can get that phi jt is poly-n in every step. And now we define psi jt to be a potential of the same form as phi j, but with smaller constant alpha. And then phi j being linear implies that the change of psi in one time step is at most cube root n, and this value is determined by the ratio between the alphas in psi and phi. And having this difference allows us to apply a bounded difference inequality with a bad event to obtain that psi jt is linear with high probability. And we can apply this to every step of the interval. So to summarize, we introduced a k-quantile process with uniform quantiles that has a gap of k times log n to the 1/k. We also proved a lower bound for any adaptive one threshold or one quantile process, and this shows an almost quadratic speedup between 1 and 2 queries, and we call this the power of 2 queries. And for k being theta log n, we recover the two-choice upper bound up to multiplicative factors. And we also get tighter upper bounds for d-thinning and for 1 plus beta with beta close to 1. Finally, we apply this to graphical allocations on dense expander graphs, for which we prove log n for two-choice. There are several possible extensions. For example, one could prove matching lower bounds for adaptive k-quantile, for k being at least 2, or prove similar upper bounds for the k-threshold process. And there are several settings in which analyzing two-choice might be interesting, such as two-choice with noise. Thank you very much for listening.